All right, so that was a quick one. Let's hope you've carried straight on to this one, which then puts that value at risk modeling into practice so you can see it illustrated. So first of all, I'll show you the Excel spreadsheet here, and we're going to use these Bank of England rates. There are 2,209 of them, because the first row, oops, sorry, let's just go up like this. First row is the date there. These are our risk factors. And these are the changes we looked at already. So this was from the 4th to the 5th for different maturities. And we have 2,208 of these because we lost one. This starts on the 5th. Bank of England rates here start on the 4th. And we can compute the correlations. We're not going to use those here, but I just thought I would show them to you because they're very large, right? So the correlation between the daily basis point changes in the, that's what you can see here. See this Corel command. They are very highly correlated. Actually, doesn't really matter, but there was zero data in the later ones there. But as the difference between them falls, so for example, this is the correlation between the 1 year and the 11-year rate, it's only 0.754. But the correlation is almost perfect between the 1 year rate and the 2 year rate. Likewise, we calculate the covariances. Here they are. And then we have the representation of our portfolio. Remember, it's completely represented by a PVO1 vector, and this is in thousands of dollars. Okay, that's enough. I'm not going to show you any more of that. I'll come back to this spreadsheet. And now I'm going to be talking about this value at risk for a gilts portfolio. So this is the evolution of the Bank of England spot curve. And we're looking at the Bank of England itself, who has issued a gilts portfolio, and it has a PVO1 vector that represents its current position on all those gilts. And we're going to map them. Actually, I'm not going to go through the mapping. It's a bit too complex, but I've given you the mapped PVO1 vector already. So neither do you need to do the mapping for the cash flows and coming at all different points. Neither do you need to calculate the PVO1. I've given you that vector of PVO1s. So gilts are, of course, UK government bonds, and they have various different maturities. This evolution just picks out 1, 5, 10, 15, 20, 25 years, but actually the risk factors we choose are going to be 50 different risk factors at 6 months, 1 year, 18 months, and so forth. And this is the PV1 vector of cash flow sensitivities after mapping to these vertices. And it's on the 30th of September. Sorry, there's a typo there. I'll collect it later. It's the 30th of September. And you can see that we have negative PVO1, which correspond to positive cash flows up to about 10 years, and positive PVO1, which correspond to negative cash flows, net mapped cash flows, above 10 years. So what this tells us is that if there's a 1 basis point increase, we will lose money on these short term, but we will make money on the long term. So suppose all these interest rates increase by 1 basis point. If they all increase by 1 basis point, but of course they don't, but suppose they all increased, the whole yield curve shifted up 1 basis point, then we would lose $2,000 on the mapped cash flow to the 6 months, we'd lose nearly $2,000 on the mapped cash flow to the 1 year. We'd lose nearly $4,000, sorry, not dollars, GBP now because it's gilts, okay. Nearly £4,000 sterling for the mapped cash flow at 4 years, but we would make a profit of nearly £6,000 sterling on the 25-year mapped cash flows. So what are we betting on? Are we looking at parallel shift up, parallel shift down, or a tilt where some go up and some go down? What would give us profits on all the cash flows? Well, we want above 10, we want them to go up because that's when we get a profit. But below 10, we don't want them to go up because we make a loss. So we want them to go down. So we want not a parallel shift in 1 basis point, but we want a tilt where the short rates are going to go down and the long rates are going to go up. So the answer to this is 3. Now for the normal VaR, the variance of the daily P&L is the usual formula where P is the PBO1 vector given on this slide here. And we can get the covariance matrix with the VaR command. And then we're going to use the mmult command for this complex quadratic form. Then we're going to take the square root. That'll give us the standard deviation of the daily P&L. And then we're going to apply the normal VaR formula and the usual square root of time rule. And that'll give us the 1% 10-day normal VaR. And this is the result. I'll show you how it's calculated in Excel. For the historical VaR, on each day t in our data set, we'll multiply that p vector by the actual basis point changes, those row vectors that we saw. And so there were 2,208 rows in the spreadsheet for the basis point changes. So we do it for every day. T equals 1 to 2,208. And then we get a whole vector of daily changes in our cash flow portfolio with 228 entries. And so it's quite a lot. We can apply the percentile function because you know with historical VaR you do need quite a lot of data, but 2,208 is quite a lot. It gives us relative accuracy. And so with the percentile function, we get the 1% quantile, which is minus 598,309 pounds sterling. But we take minus the percentile, remember, so we multiply that by -1, and then we scale to find the 10-day VaR here of 1962959 GBP. So the only thing remaining now is to go back to our spreadsheet where this is in Excel workbook 5. So we've got the covariance matrix here, which is computed using the VaR command. And as I said, I changed the data, so this should actually be 2208, but it doesn't make any difference to the result, so that's fine. So these are the covariances. We can't tell what's big or small, you know, just because it's 21.623, it doesn't tell us really much about the correlation. That's why I put those correlations in there. But it's the covariance matrix we need for the normal VaR. This is the PBO1 vector, which you can change. Anything red you can change. So you can calculate using the same data in the covariance matrix or in the basis point changes. If you're using historical VaR, you can look at the VaR for any portfolio just by changing the entries in column B. And these will come up in the plot, of course. So if I do that, you see this suddenly becomes 1. Finally, the VaR calculation. Well, let's first of all look at the normal VaR. We have to use the mmult command. So here, this bit starting here, first of all, we're going to do P prime V. No, actually, first of all, sorry, we do V P prime. Sorry, VP. That's this bit here. You see there's a comma there, and this is M mult VP. All right. That's the first M mult command. Then we do M mult P prime times this, which is M mult, now the red bracket, P prime, now the comma's here, and it's what we got in the first stage. So it's 2 M mults with transpose. Take the square root, multiply by the norms inv of whatever our significance level, that's in E2, use the square root of time rule, remembering this 1000 comes in here because the PVO1 vector was in 1000 pounds, not dollars. Okay, so the square root of E3 is the square root of time rule, and 1000 gives you the right answer in pounds. Now, to get the P&L vector, the delta P vector, we use the sum product, and we have to keep the P vector constant in that sum product. So I've used dollars here by pressing F4. And so the transpose of PVO1, and you don't want that to change as you roll it down, so you put dollars there. Remember, this PVO1 sheet cells B2 to cell B50. These are fixed, and these are these cells here. This is B2 going down to B50. So we fix those, and what we don't change is the row that we take from the changes data point. That's why I have to transpose that PVO1 vector, because we read through the changes as rows, and you can only do the sum product of 2 row vectors. Okay, I didn't have to use the sum product. I could have done this with an M mult command, but I chose not to. So when we build down, this bit doesn't change, but now we've gone to the next row in the basis point changes. So we've moved from this row to this row. And we continue down the whole lot. We then apply the percentile function multiplied by -1. You can see that -1 there. Use the square root of time rule and multiply by 1000 to get it into pounds. And depending on the significance level and the risk horizon, the risk horizon just scales everything. So if you had 1 day, you still see the relative size here. Whether it's 1 day or 30 days, the normal VaR is always going to be less than the historical VaR at 1%, but at some significance levels, like 5%, let's have a look. Here, the normal VaR is greater than the historical VaR. And that's because a historical VaR gives a P&L distribution that you put all these into the column B into a histogram, you'd see it has that leptokurtic quality of the narrow arch and longer, thinner tails than the normal distribution. That's it for now, and see you in the next topic.